and bases with each other. Okay. For you guys, you know what an acid is because you will be seeing the H in front, and you should officially be seeing the AQ for a phase. You now know you have an acid. So if you look at a reaction and you see an H in front and an AQ for either of your reactants, you should immediately be thinking neutralization. Immediately. Okay? It might not be, but that's at least a solid hint. Okay? After that, your base has OH. Okay? So if you have OH and you have that acid, you can run it. Okay? And you go through the reaction, you'll produce water and the remaining salt, or the leftover pieces of the salt. This looks kind of familiar already. This looks kind of like where I had A bound to B, right? Plus C bound to D to produce AD and CB. Does everybody see that? So the A here is that. The B here is there. C, D. Does everybody see the parallels? Okay. Well, what kind of reaction did I just draw out with all the letters underneath? Double replacement. What is a neutralization? A double replacement. Why do we call it a neutralization instead of just calling it a double replacement? Okay. It involves acids and bases. Prior to this class, has anybody heard or had heard the term acid or base? Okay. Probably everybody's shaking their head. Had anybody heard of double replacement? No. Why is that? Acids and bases are our most common chemistry. Okay. They're the easiest things to call attention to because we can see the damage that they do almost instantly when they come in contact with us. So historically, acids and bases are a very important kind of class of chemicals, which means when we look at reacting an acid with a base, we'll kind of pay homage to that history of acids and bases and call it a neutralization, a separate name to kind of set it apart from the other reactions. Okay? It is still a double replacement, it's just better classified as a neutralization. Okay? To go through and do these, we have to do the same process that we've done with everything else. You have to know your nomenclature. Okay, so if we were going to predict the reaction, predict the product of the complete neutralization of sulfuric acid with potassium hydroxide. Okay, sulfuric acid. What is the formula? So as a big hint, it says acid, which means H. Okay? And then it has to end with AQ. Okay? The next part is trying to interpret the sulfuric. What is our interpretation of the sulfuric? Okay? We have the sulfur in the name, so we're already thinking S. Okay? Should it just be S? If it was just S, that's hydrogen and sulfur, and that's it. That would be a binary acid. Binary acids get named with hydro as the prefix. Is this hydrosulfuric acid? No. Which means it's not just hydrogen and sulfur, it's a ternary acid, which means that needs to have an oxygen with it. Okay. Now the question is, how many oxygens should it have? Should it be 3 or should it be 4? Well, it'd be nice if the name gave us some information about it. It does. This ic ending only comes from 8s. Okay. So the complex ion that generated this acid was sulf8. Well, what is the formula for sulfate? SO4. Okay. For those of you wondering how anybody would know that, you were asked to memorize that. Okay. What charge does sulfate have? A -2. We can now combine all that information down below. We'd have our SO4. Sulfate has a -2 charge. Hydrogen has a +1. Is that formula balanced? No. How do I balance that formula? I need 2 hydrogens. I now have sulfuric acid. All right? How are we doing with that? Okay. From what I'm seeing, the 2 people that already knew the content are saying they're okay with it. And everybody else is staying silent. Does that mean you're tired, it's Tuesday, and you just wish you were still on spring break? Or does that mean you get it and you're okay and let's just move on? A little bit of both. Okay. So we'll continue with potassium hydroxide. So we're looking at a plus. What is the symbol for potassium? K. What is the symbol for hydroxide? OH. Right. What is the charge on hydroxide? -1. What is the charge on potassium? +1. Is that formula correct? Yes. What is the phase for potassium hydroxide? All right, so I've heard an aqueous, so we'll start with that. We'll put you on the spot a little bit. Why do you want to say aqueous?
Because hydroxide, for the H, it would be an acid.
So for the acid, I agree. H2SO4, because it says acid, we should be writing the aqueous. I will agree with that. But I didn't ask about the acid, I asked about potassium hydroxide. Any ideas? You can say no, that's okay. I like the pointing, Ashton. What do you got?
No, I'm just saying, like, because my hydroxide doesn't that. Well, I can't really.
The hydroxide doesn't have a rule that it has to be aqueous, like the acid did. Okay. Probably most people are going to go through and write aqueous on there. Okay. You're doing that because of experience and experience alone, because nothing in the statement above specifies the phase. If you look up potassium hydroxide is actually a solid. Okay? But if I'm going to react potassium hydroxide with something else, I want to get it into the same phase so that I get a better reaction. Okay? If we think about burning a substance, okay, I take a block of wood and I try and ignite it on fire. Okay, it burns for a while, but if I take the same mass of wood and I turn it into sawdust, okay, and now I toss the sawdust in the air and try and light it on fire, what happens? You're going to get a pretty big fireball pretty darn quickly. Why? More oxygen and more heat can contact each of the individual pieces of wood, which means they all ignite on fire. Why did the block of wood not? Can the inside of the block of wood interact with the fire? No. So if we can expose every single molecule to the reaction, we can speed the reaction along. So here, if I put in potassium hydroxide in the solid phase, that's not going to speed the reaction along. That's actually going to slow it down, because the middle of that potassium hydroxide can't interact with the acid. All right? But because the question doesn't specify it, what should you do? Not specify it. You don't know. Okay? If the content isn't there, don't worry about it. Okay? Next part. We need to go through our exchange. What is B in our equation? Right? B fits with the OH. There's our hydroxide. B is our potassium. So we could write our potassium. What is A? The A is now our sulfate. Right? I don't have any information about the phases, so let's not worry about that yet. Right? And what else? What else am I going to produce? HOH, which is water. I could write it as HOH or I could write it as H2O. If you have to move into more advanced chemistries, depending on your instructor, they tend to freak out at HOH. I used to be one of those people. I think HOH makes more sense to see the double replacement. So it's entirely up to you. Okay? Do you know the phase on H2O? Probably, but again, you're kind of guessing at it. What phase would you guess this to be? Probably a liquid. Okay? It's certainly not going to be a solid, okay? But it could potentially be a gas. Acid-base reactions are exothermic. They release lots of heat. That heat could be enough to cause the water to boil, and we could be looking at the gas phase. If we double back to KSO4, okay, our potassium sulfate, before we even look at the phase, what we want to do is address, did I do that correctly? What is the charge on potassium? A +1. The charge on sulfate? A -2. Is that formula correct? No. What do I need to do to fix it? 2 potassiums. Right, make sense? Right. I now have my equation. Is the equation balanced? Right, to balance, we'd go through and look at each element and decide all the way through. We could go through and balance it as hydrogen. I'm going to argue that balancing it as hydrogen doesn't make sense because I would get 3 hydrogens here, okay, and I only appear to get 2 hydrogens out here, and that's going to be weird to balance. Instead of balancing it as hydrogen, I'll balance it as the complex ions first. Sulfate, right? How many sulfates do I have? 1 and 1. So sulfate's balanced. How about potassium? 1 and 2. How do I fix it?
So what do you call 1 in front of the potassium on the left?
How many potassiums do I have on the left now? Still 1.
So you would need 2 then.
I would need a 2. Okay, perfect. So I now have 2 potassiums. My sulfate were balanced. And now here's where I would make my jump. Instead of balancing this as oxygen and hydrogen, I'm going to balance it as hydroxide. Because I've written this as HOH, I can see that I have hydroxide in water. This is one of the reasons why I like the HOH setup. How many hydroxides do we have here? How many do we have? We have 2 on the left-hand side. How many on the right? Only 1. It needs to be 2. How do I fix that? Put a 2 in front. I now have 2 hydroxides on the right. And now let's go back and look at the hydrogen. How many hydrogens do I have on the left? 2. Good answer. Why are you not telling me 4? Because this hydrogen was part of hydroxide. So there's only 2 on the left. How many on the right?
2.
2. Because the other 2 are occupied in the hydroxide. Kind of makes sense? Okay. We could have now done it also as just hydrogen on all sides, and it still would have come out correct because we've done everything else. So hydrogen tends to be one of those elements to leave for the very end because we hope everything else balances before we have to deal with the hydrogen. Kind of makes sense? Questions? It's right after spring break, so I'm trying to ease into this slowly. Hopefully. We're going too slow? No. Okay. So, now we're going to make it significantly more difficult. Because I said we should ignore the phases for this species and for this species, because neither were provided, right? Neither were provided, correct?
Yes.
There's an inflection there for the question mark. What type of reaction did we say the neutralization actually was? Double replacement. And what's the issue with the double replacement reactions? Like, that was before spring break. You didn't actually tell me the issue. Yeah, I know. Some people did well on the test. You can jump in. What's our problem with our double replacement reactions? It's a little bit trickier to deal with. You are required to predict phases. Right? If a neutralization is a double replacement, what does that mean? You need to predict the phases for the neutralization as well. Okay? How would we predict the phases? Well, how do we do it for the double replacement? Oh, there we go, solubility rules. Right? We would have to know the solubility rules. Okay? You're like, well, I didn't memorize those. That's good. I didn't want you to memorize those. Okay? I wanted you to think about those and hold on to them and apply them. There were a couple I told you that you should memorize, okay? But I did not require it. What did I do to prevent you from requiring it? I put it on the test. You mean the test that you conveniently all just got back? Yeah, that test. How about let's take a look at that front page of that test and see what it says for our solubility rules. And see if we can use those solubility rules to predict our phases for either the potassium hydroxide or the potassium sulfate. Oh, that's a good sign. I like that. Which one do you want to do, A or B? A. All right, so we look at those rules, and what are we trying to find? We're trying to find either potassium or hydroxide. So in the rules on that first page, do you see anything about potassium or hydroxide? Okay, there's two answers to that question, yes and no, and believe it or not, I will accept both answers. You don't. You don't. I heard somebody say a yes over here, maybe. Okay, so we have a yes and a no. I said both answers were acceptable. Why are you saying yes? Because presumably everybody understands why the no. They don't see K, right? Okay, so why are you saying yes?
It says group 1 metals.
It says group 1 metals. What are group 1 metals? Group 1 metals are the first column of the periodic table. Right? And on our periodic table, it actually says group 1 on it. And we look within that column, what metal happens to be in that column? Potassium. Okay? So it is there. It's in rule number 1. What does rule number 1 say? It is always soluble, which means the phase is aqueous. Okay? Anytime I see potassium, it needs to be aqueous. I've now specified the phases. I've balanced the equation. Everything is sweet and golden and right in the world within this room. Make sense? We okay? You guys want to look at the combustion? Because I kind of don't want to. I mean, it's important-ish, but not important enough that I want to talk about it again. What do you guys want? Is that a yes, you want to talk about it, or no? A sure? Okay, that's sort of a yes. Okay. When we're looking at a combustion reaction, we're taking any organic material. So if you have to move up to organic chemistry, you're looking at carbon and hydrogen, okay, at a bare minimum. So if you move into 151 or 152, they may do combustion reactions with more complex organic materials, but it minimally has carbon and hydrogen. We will react it with oxygen gas, and every single time it will produce carbon dioxide and water. Okay? This is one that you're required to have memorized, because it's always this. That's what it does. Okay? So if I take some organic compound, in this case C4H10, also known as butane, don't worry about it. Okay? I react that with oxygen gas. Oxygen gas is O2. How do I know it needs to be O2? Because it's diatomic. The whole have no fear of ice-cold beer. to produce CO2 and water, H2O. Okay? Those are now both nomenclature from this. Okay? You'll notice I didn't specify any phases. Don't stress about the phases when it comes to the combustion reaction at all. Okay? Don't worry about it. The part that the combustion reaction really becomes tricky with is actually balancing it. Okay? So let's go through and take a look at balancing. How do we start? Probably carbon. I like doing that behind your hand, making it sound like it wasn't you.
That's how I throw people off.
How many carbons on the left-hand side of the equation? 4. On the right-hand side? 1. Is that balanced?
Nope.
No. Fix it.
Add more to the right.
I need to put a 4 on the right. That then means I have 4 CO2. So I'm now showing that work, changing that 1 to a 4. Okay. The next one I'll balance will be hydrogen. How many hydrogens on the left?
10.
Hydrogens on the right. Can I make 10 equal to 2? You should say no to that. You can make 2 equal to 10. Sorry, that's how I meant to say it. How do I make the 2 equal to 10? I need 5 water molecules. That makes that 2 a 10. Make sense? Okay. And then we save for last the oxygen. And we save that one for last because oxygen shows up in 3 different places. That makes it difficult to balance. Okay. So what we're hoping by saving it for the end is that everything else balances out and the oxygen is now done on its own. We don't have to worry about it. Okay. And we already see people shaking their head because you can do that math. Oxygen's on the left. 2 oxygens on the right. 8 plus 5 equals 13. Can I make 2 equal to 13? Okay. I would have to use a fraction, which means I would have to use a fraction of a molecule. Can I use a fraction of a molecule? No. Okay. I cannot use fractions of molecules. That's not allowed. So now this seems to be impossible to balance. Okay. It's impossible to balance at this stage. Okay. But what we can go through and do is get this 13 to become an even number. Because once it's an even number, then it can balance with an even 2 here, right? How can I make that 13 even? We'll just add 1. Okay, I can't just add 1. That doesn't work because that's going to mess everything else up. So I need to go through and get that to an even number where it doesn't drastically affect just one of those 2 numbers. It has to affect both, and it has to affect both of those numbers equally. How can I do that? Do what?
Times everything by 13. Or by 2.
13 times 13 is 169. Good, that's what I thought it was. I wasn't positive. Okay. So 169, what's the issue with 169?
Still.
That's still odd. So multiplying by 13 doesn't work. How about we just multiply by 2? The whole point was to get to an even number. Let's multiply by the smallest even number possible. So if we multiply by 2, what happens? Okay. And yes, this is now a giant mess, but if I'm going to multiply one side by 2, what do I have to do the other side?
By 2.
Multiply the other side by 2 as well. Okay? Which means the number in front of C4H10 is 2. Okay? We're going to leave the oxygen alone for the moment because we haven't done anything with that number yet. We don't know what belongs there. Okay? I have done something with the 4. I placed a number there intentionally. So that's going to get multiplied by 2. 4 times 2 is 8. 5 times 2. 10. Spring break didn't break you that much. You're okay. Okay. What does that then mean? All that balancing work that I did is now incorrect because I certainly don't have 4 carbons on the left, right? Okay. So I hit an issue. I said, well, screw it. I'm going to get it to an even number. I'm going to multiply everything by 2, but that process then negates all the work I've done, which means I get to restart. The hope is that after restarting, it will magically all work out for me, and I don't have to stress about it. So let's see. Carbons on the left. Carbons on the right. Not oxygen. What's the other one? Hydrogen. I get 20 and 20. Okay, so that's neat. And multiplying it by 2, it didn't actually mess with those. It just scaled them up. Okay, oxygen's on the left. Currently just 2. Oxygen's on the right. Well, there's 16 because 8 in the 2 plus 10, which gets me 26. Is 26 an even number? Yes, that's convenient because now I can make the 2 into a 26 by doing what? By putting a 13 in front. And that 2 now becomes 26. So is my oxygen then balanced?
Yeah.
Yep. Remember that part when we talked about it and I said the next step of this is to do what? Okay, so you just made this a longer process. That's okay. We get to do it again. Carbons on the left. 8 carbons on the right. Hydrogen's on the left. Hydrogen's on the right. Oxygen's on the left. 26, because 13 times 2 is 26. That's probably one that admittedly I would write out, believe it or not. Okay. Oxygen's on the right. Don't tell me 26. 16 plus 10 equals 26 for the oxygen balance. Yes. According to the procedure that I gave you at the beginning of the semester, or not beginning of the semester, but beginning of this unit, what should you do now? You do it again. Okay? So let's do it again. But we've gotten too used to going in the same patterns, so let's change it up this time. I don't want to go in the exact same pattern because I've memorized that sequence of numbers now. So I'm going to switch it up and start with hydrogen. Hydrogen on the right. 20. Hydrogen on the left. And now I'm going to balance. Oh, I actually was going to do oxygen. Dang it. Oxygen's on the right. 16 plus 10 gets me 26. Oxygen's on the left. 26 carbons. 8 and 8. Make sense? Okay. I do want to address this as well because the textbook goes through and shows very similar work, if not identical. Okay. And everybody looks at it and goes, oh, well, they had just that sequence of numbers, so I'm just going to write those sequence of numbers down. The textbook is showing you the final answer. Okay. The process on how we did this was slowly, stepwise, and looking through at each individual one. Don't just start drawing out the final answer because that's what it shows. The only reason you know the final answer is because you've done all the other work. Okay, make sense? Okay. No. Temperature. Okay. Temperature is a measure of your average kinetic energy in an individual sample. Okay. So if we take a look at 2 samples, okay, one with ice water in it and one with boiling water, we can get a measure or a representation of the average kinetic energy. That representation happens to do with where the liquid in a glass tube falls based off of the internal pressure. Okay? Because this observation was made multiple different times by multiple different people in multiple different areas, and then those people got together and then yelled and complained at each other and nobody changed, we have multiple temperature systems. That's where we get Fahrenheit, Celsius, and Kelvin. Okay? Fahrenheit is part of the English or imperial system, which is really now just American. Celsius tends to be fairly commonly used and is part of the SI system. Kelvin is pretty much exclusively used in science. Why do we not just go directly to Kelvin? because most people would freak out and think it was really hot outside if we said it was 273 Kelvin. Oh my God, I don't want to go outside, I'm going to melt off. Except 273 Kelvin is freezing. Okay, it is the freezing point of water. Okay, so that becomes a little bit more challenging to deal with. Okay, so because of these number systems, we've invented other ways to evaluate them. Because we have these different evaluations, we then have to be able to convert between them. Yay! Okay. The big temperature ranges that come out of this: Fahrenheit freezing is 32, water boils at 212, degrees Celsius is 0 and 100. That's kind of nice. You get this kind of powers of 10. And then Kelvin gets all sorts of weird. Freezing is 273 Kelvin, and it boils at 373 Kelvin. A slight typo on the bottom here. You'll notice that all of those have degrees next to them, including the Kelvin. That is actually wrong. Kelvin is not a degree system. Kelvin is an absolute system. There are no degrees. It's just capital K, Kelvin. Okay. Subtle thing, don't stress about it, but that's to be more correct. Okay. What do we do for our conversions? Okay. Just like most of our conversions, these are really straightforward and simple to convert between. Celsius and Fahrenheit have, that was a joke. Celsius and Fahrenheit have very little representations between them, so we have to go through some stupidly convoluted formula to go through and calculate it. Right? Why? Because scientists. Not science, scientists. Those stupid egomaniacal people that can't just accept the relationships. Right? Kelvin is a little bit more straightforward. All you have to do to get Kelvin is add 273 to your degrees Celsius. Officially, it's 273.15 and then a bunch of other numbers. Why is the 15 there? What is pi? Anybody else? What is pi? 3.14 blah, 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 blah. Okay. Ideally, you would have given me a string of numbers after that, not the blah, 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 blah. And I'm going to call you out for it. Some people memorize pi as 3.14. There we go, 159. Why do they? Because I'm guessing you're right, by the way. Why would someone memorize those extra digits of pi? It could go to significant figures. Okay. The argument that I would make is so that we feel smarter about ourselves. Guess why I wrote 273.15? I feel smarter about myself because I happen to memorize an extra 2 decimal places. Okay. All you need is 273. You just need your 3 sig figs. If you want to remember the 0.15 and feel smarter about yourself, you are welcome to it. Sometimes we just got to do that. Okay? Make sense? Okay. I believe the 273 one is easy enough to memorize, so that is not something I will give you on the exam. The other one I think is confusing as all crap. I will give you that on the exam. Right. Note, I'm still giving it to you on the exam, even though you all have a note card. Right. Body temperature is 98.6 degrees Fahrenheit. Do you guys want to go through and do the conversion to Celsius, or do you think you guys can do the algebra? Don't do it. Okay. The answer is 37. Okay. The next part is your heat concept. Heat is different than temperature. Temperature measures the average kinetic energy. Heat is the total kinetic energy of the sample. So these are slightly different concepts behind it. Okay. The best way to go through and describe this, as you may have seen in one of the practice exams, is looking at coffee. Okay. A drop of coffee spills in your lap. Okay. The cup of coffee spills in your lap. They're both the same temperature, and yet you're probably going to respond differently if the coffee spills in your lap. Why? They're the exact same temperature. Why should you change? And don't tell me because now your clothes are stained. That doesn't count.
More coffee.
There's more coffee. Why does that matter?
It's more heat.
It's more heat. Heat is the total energy in the system. If you have a single drop of coffee, there's a relatively small amount of total energy, even though each of the particles in there have the same average kinetic energy as in the cup. But the cup has more of those particles, which means more heat transfers to your lap and makes it a very unpleasant experience. Okay? So there's two different kind of relationships behind that. Temperature, we'll use degrees Celsius as our arbitrary unit system. Heat uses joules or calories. If you've eaten food, that was a stupid statement. We've started, we just got to go with it. If you've eaten food, packaged food, you might have seen somewhere on the side of the label that's got the nutrition label that says something about the amount of calories present. What are calories? They're a measure of the energy or the heat found within that food. That doesn't mean when you eat it you're going to necessarily get hot, but that energy, that chemical energy, you use and convert that into energy for your body to function. Okay, you control that heat energy, okay, or your body does, which is pretty neat.
For the note card, does it have to be a certain size?
3 by 5. I'll post an announcement about it and remind you periodically. Okay? So we get these two concepts for measuring the energy of a system. Okay? The big one that comes out of this is specific heat, which is a conversion factor, okay, which I'm sure everybody would love to hear about because we've got conversion factors up the yin-yang. We can look at calories being related to the mass of the substance and the temperature change. Okay? So if I take an individual sample of material and I add heat to it, okay, the amount of heat I add to that per gram of the sample to make the sample go up by 1 degree Celsius is now the specific heat. Okay? It's a big convoluted thing, but that's what it means. Okay? If I want to convert between calories and joules, two different energy systems, that's now my conversion factor. Okay? So it's up to you on what you would necessarily want to go through and use. So we could go through and run a whole bunch of conversions and calculations with this. If you have to take 151, you will do that. If you don't, we will not. But instead, I want you to be able to interpret what it means. Okay? Which of the following substances is expected to have the largest specific heat? Okay, well, let's think about what specific heat meant. I take a gram of the sample and I add heat to it. When it goes up by 1 degree Celsius, that is now its specific heat. Okay? So the specific heat is a measure of how much energy it's necessary to cause it to go up by that 1 degree. Okay? So if I took, say, I don't know, a copper pot, and I put some heat underneath it, okay, I'm going to get the temperature to go up by 1 degree Celsius with a relatively small amount of heat being added into it. Why?
Absorbs heat better.
I like where you're going, but absorbs is technically the wrong word. What did you use?
Conductor.
It conducts. It allows the heat to pass through the material very, very quickly. It conducts heat. So it allows for the transfer of the heat through. Okay? Why does it allow for the transfer of the heat through? I think you said the other important word on it.
I said absorb.
But after that, you said absorbs heat. What was the material, though?
Copper.
I said copper. I thought you said something else. Maybe I was wrong. What is copper? A metal. Okay. What do metals do? Conduct heat, which means all metals should have similar properties when it comes to their specific heat. Okay. The amount of energy necessary to put in was what? A lot or a little to get the heat to pass through the metal? Very small amount, which means our specific heat is small. Okay, I'm asking for the largest specific heat. Thanks, Mike. I just went through and explained how to get the smallest, but now I'm asking for the largest. Okay, well, is there a material that if I put heat underneath it, it doesn't allow for the passage of that energy? Anybody like pulled cookies out of the oven? Just barehanded, just grab the plate and just pull that out, roar, and just smash the plate in their face with all the cookies. What do you put on your hand? A glove. What is the glove doing? It protects you. It insulates you from the heat. What is the glove made out of? Cloth. What is made of cloth? Cloth is cotton. What comes from cotton? Or where's cotton coming from? Plants. And plants are a form of organic material. And organic material is made of carbon, which happens to be a non-metal. Right there. Thank you. Because it's on the right-hand side of that staircase, it's now an insulator as a non-metal. So it doesn't allow for the passage of heat. So metals allow for the passage of heat. They get very low specific heats. Non-metals, because they insulate, get very high specific heats. Okay? The other common material used for those gloves? Like the fancy kind of rubbery gloves? Silicone. Where is that? To the right of our staircase again. It's actually a metalloid. One of its properties is it doesn't conduct heat very well. Okay? So if we go back to our list, largest specific heat, we just came up with the answer. It needs to be the non-metal. Okay? Why is this question now tricky with the answer choices? When you look at the periodic table, you can tell me which one's a metal and a non-metal, right? How? The staircase. Left of the staircase, okay, it's a metal. To the right, non-metal. So when you look at the periodic table, you can find Ca, right? Where is Ca? On the metal side. So it conducts, I would expect, a very low specific heat. Cr. Metal. Okay. Copper. Why is that one weird? Where does it say copper on the periodic table? Cu. Does copper say Cu? No. What makes this question a little bit more challenging? You have to know the symbols. It's testing on nomenclature as well as on specific heat. Okay? Two different concepts. Cu, metal. Pb, metal. It's also to the left of the staircase. Carbon, C, non-metal. Carbon's our answer. Make sense? What if we flipped it to smallest specific heat? What would I have to change with the answer choices? For it to be the smallest specific heat, our answer needs to be a metal. Would you be able to answer this question then? No, why not? Too many metals. Okay? I don't expect you to be able to distinguish specifically how those specific heats change within periodic table. I expect you to know metal versus non-metal. So I would have to go back through and change a lot of those metals into non-metals. Okay? Make sense? Okay. Physical laws, we've got some laws back in chapter 3 which you read about. We get conservation of mass. Okay, we can't create or destroy matter, okay, which means if we look at a chemical equation, I can use the chemical equation to predict the amount of something to come out of this. Okay? If I put in, and this is horribly wrong, so don't trust it, 2 grams of oxygen and 4 grams of oxygen, and we assume that this thing was correct, how much water should I produce? 6 grams. Conservation of mass. I started with 6 grams. What did I better end with? 6 grams. Okay? That's what conservation of mass means. It allows me to predict the mass of the product. Sort of. Let's move to the bottom one. Let's do something similar. Let's take 6 grams of wood, 2 grams of oxygen. How much gas is made?
Well, that's wood.
The wood was 6 grams. So I've got a verdict that 8 grams of gas was made. If 8 grams of gas was made, how much water was made? 0 grams of water. But according to this equation, is water produced? Yes. Can that possibly be 8 grams of gas? No, because then the equation's invalid. So how much gas was produced? Those of you being like, I don't know, that's kind of a hard question. That's because it's an impossible question. We can't figure it out. The only time we can predict how much is actually produced is when we know all but one of the variables. So in the previous question with hydrogen, oxygen, and water, you were given 2 of 3. You could solve for the third. And the bottom one, I've given you 2 of 4. You can't solve for the missing 2. You would need more information. So if instead I went through and then said, you produced 3 grams of water, can you now tell me how much gas was produced? How much was produced? 5 grams. Make sense? So conservation of mass allows you to predict products to a certain extent, as long as you're only missing a single thing. If you're missing more than one, you don't have enough information to solve. Okay? Einstein came through and said mass and energy were related to each other. Okay? Because of that, that then means we can't destroy energy as well. So the law that we actually deal with is the law of conservation of mass and energy because they're related. Okay? So that means when you produce some energy, that energy goes somewhere. It doesn't just disappear. It comes off as something. We want to try and capture that and do something with it. We'll always end up losing some, and that starts adding on other laws of thermodynamics into this, okay, that you don't need to stress about. But our energy is constant through our reactions. Our law of conservation comes in handy when we think about all the forms of energy. What are the forms of energy? Wow, you guys were really fast at that. Yeah. Light, heat, chemical, electrical, mechanical, and nuclear. For those that didn't hear you, shout that all out at home, okay? Just in case they didn't hear that, because you guys were so good and on top of that. Those are our bulk forms of energy within chemistry. When we think about the lights in this room, how did we get that light energy? We got that light energy from the electricity. Where did we get the electricity from? Any ideas? Where did we get the electricity from? Never thought about that. Okay, that's interesting. Okay. We could say it came from a solar plant. Okay. So if it came from a solar plant, that electrical energy came from light energy. That seems a bit silly, but that's actually one of the shortest loops. Why would we say that's silly? Well, you had light, and you converted it into electrical just to make more light? That's dumb. Okay. Do you want light in this room? Yeah. The way we get light in this room is by doing that. Or we cut a giant hole in the ceiling. Okay. Those are our 2 options. Okay. So yeah, that works. What if it didn't come from solar? What's another place? Okay, mechanical. Where's our mechanical coming from? Okay. We could look at a dam. We're talking about hydroelectric. Okay. Water falls over the dam, causing a turbine to move, which generates electrical energy. So we have the mechanical energy there from hydroelectric. That works. Okay. Both solar and the hydroelectric together make up some stupidly small percentage of our energy, though. Nuclear. What's happening with our nuclear? It is actually coming from a mechanical. It is a turbine moving. Okay. That turbine moving was actually due to water boiling, which was heat. Where did that heat come from? Nuclear. Every single one of those arrows results in a conversion of the energy from one state to another state. Each of those conversions results in the loss of energy. Which means with that many arrows, yes, nuclear is a great way to produce energy, but I have so many individual steps, I'm losing energy at each of those stages that don't actually make it to the light. I have to produce in excess of what is necessary. The shortest jump we can get is the best process for us to go through and do. So nuclear could work, which also makes up a very tiny portion of this, so I'm going to get rid of all nuclear. What's the last place we could get energy from? Petroleum. Right? Believe it or not, that's what, or petroleum or coal. What are those? We're getting the electrical, actually again, from a mechanical system. What's that mechanical system? It's a turbine. A turbine that's moving due to boiling water. Right? That boiling water was boiling because of explosions in our chemical energy. Right? We're pretty archaic in our systems. All of our electrical energy is coming pretty much all the way back to this mechanical aspect, and really the mechanical aspect to boil water. That is our energy future right now, is how do we boil water efficiently. Okay? That's pretty horrible. Okay? This is why solar becomes more important. This is why hydroelectric can become more important. Both of those have issues as well. Okay? So we're looking at how we can convert between those stages. So our mechanical energy in our car, how are we getting the mechanical energy? We're doing mini explosions with gasoline. Okay? If we burned all of the gasoline in an instant in our car, we'd all be dead because there's lots of energy stored in those chemicals. That's why we do very, very small amounts in a controlled burst. By controlling the explosion, we only make a piston move. Okay? But if I can get the piston to move fast enough and frequently enough and convert that energy across through the transmission in the car, I can generate motion for the car, which is pretty sweet. Okay? You can do the same thing with a cannonball. Cannonball is doing the exact same thing. The piston is the cannonball. Except here, we're not trying to control it very tiny. We're doing a massive explosion, which causes it to launch the cannonball. The last one, all of us are doing, even as you're sitting there staring at me, ATP to ADP. Biologists? No biologists? Okay. When you get into biology, did you hear about ATP and ADP? Yeah, what is ATP? It's energy. It's the energy for everything. They just say it's ATP. What is ATP? Adenosine triphosphate. That's this thing. What is ADP? Adenosine diphosphate. Well, you just change the T to a D and we exist. No. You get rid of those three atoms. We change the phosphate structure. By removing those three atoms, we generate enough energy to live. Pretty cool. Okay, and with that, we'll go ahead and end for today, and then we're pretty much moving into chapter 8 and 9, which is our